The morning light filtered through the windows of the Naval Technical Research Laboratory in Yokosuka on a spring day in 1942. Inside a sealed testing chamber, 3 of Japan's finest electronics engineers stood before an object that had arrived 3 weeks earlier from the Philippines. An American SCR-268 radar set. Intact. Operational. Impossible. They had been told to evaluate it, to understand it, to copy it if they could. But as Chief Engineer Nakamura Hiroshi removed the first access panel and peered inside at the circuitry, something in his expression changed. He said nothing for a long moment. Then, very quietly, he spoke words that would be recorded in the laboratory's classified report. "We are not 8 years behind. We are 8 years behind in manufacturing capability alone. In system integration, perhaps more." If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This is not a story about a radar. This is a story about the moment Japanese military leadership confronted a truth they had spent years denying: that the war they thought they were winning through superior spirit and tactical brilliance was already lost. Lost not on battlefields, but in factories. Lost not to American soldiers, but to American electricians and assembly line workers who could build in a month what Japan's best engineers needed a year to prototype. The SCR-268 was not just a piece of equipment, it was a message written in copper wire and vacuum tubes, a declaration that American industrial capability had evolved beyond anything the Japanese military-industrial complex could match, and the engineers who studied it became unwilling messengers of their own nation's defeat. Today, we explore how a captured fire control radar became the mirror in which Imperial Japan saw its future and found only darkness staring back. The SCR-268 Searchlight Control Radar first entered service with the United States Army in 1940. Designed by engineers at Fort Monmouth's Signal Corps Laboratories under the direction of Paul Watson, it represented America's first practical radar system for directing anti-aircraft fire. Operating at 200 MHz with a wavelength of 1.5 meters, it could detect aircraft at ranges up to 20 miles and guide searchlights and anti-aircraft guns with unprecedented accuracy. By every traditional measure, it was not revolutionary technology. Britain, Germany, and even Japan had developed radar systems by 1940. Dr. Hidetsugu Yagi, a Japanese electrical engineer, had invented the directional antenna that bore his name. Japanese researchers at the Japan Radio Company had produced a cavity magnetron as early as 1937, actually ahead of British developments. Japan understood the physics. Japan had talented engineers. Japan knew radar was important. But here is what matters. The SCR-268 was not designed to be elegant. It was designed to be producible. It was designed to work, reliably, in the hands of soldiers who were not engineers. It was designed to be manufactured by the thousands and deployed everywhere American forces operated. And by 1942, when that captured radar set reached Yokosuka, exactly that was happening. The war in the Pacific had begun with Japanese victories that shocked the world. Pearl Harbor on December 7, 1941, the fall of Singapore on February 15, 1942, the Philippines surrendered on May 6, 1942. In those early months, Japanese forces seemed unstoppable, sweeping across Southeast Asia and the Western Pacific with a speed that suggested invincibility. But beneath the surface, Japanese military planners harbored deep concerns. They understood that Japan's industrial capacity was a fraction of America's. They knew the resource base was insufficient for a prolonged war. The entire strategy had been built on a gamble. Strike hard, strike fast, win quickly before American industrial might could be brought to bear. Force a negotiated peace before the true weight of American production could tip the scales. The intriguing truth: Japanese military intelligence had studied American industry extensively. They knew about Detroit's automotive production. They understood that American factories could be converted for war production, but they had made a catastrophic miscalculation. They believed American society was too soft, too divided, too individualistic to sustain the kind of total war mobilization that victory would require. They believed that the spirit of Bushido, the warrior's code that prioritized death over dishonor, would overcome material disadvantage. The SCR-268 radar set captured at Corregidor proved them wrong in ways that went beyond any single battle outcome. Consider the circumstances of its capture. The Philippines campaign had been a defensive disaster for American forces. General Douglas MacArthur's forces, caught off guard by Japanese attacks just hours after Pearl Harbor, had been pushed back onto the Bataan Peninsula. Among the American units fighting on Bataan was a small Marine detachment operating an SCR-270 long-range radar for early warning. They also had several SCR-268 sets for directing anti-aircraft fire. As Bataan fell on April 9, 1942, American forces were ordered to destroy their equipment rather than let it fall into Japanese hands. The Marines destroyed their SCR-270, burning the antenna and pushing the radar vans into Manila Bay. They found an Army SCR-268 unit near Cabcaben Airfield and helped those soldiers destroy that radar as well, burning the technical manuals before Japanese forces could capture them. But not every radar was destroyed. The Japanese advance was swift. Some American positions were overrun before demolition could be completed, and so it was that intact SCR-268 radars fell into Japanese hands. Not as burned wreckage, not as fragments, but as working systems, complete with technical documentation. The Japanese military recognized the intelligence value immediately. These were not the crude early warning sets American forces had been using in the Philippines. These were fire control systems capable of directing nighttime anti-aircraft fire with accuracy that Japanese aircrews had experienced firsthand. Understanding how they worked became a top priority. The radar was shipped to Japan under heavy security. It arrived at the Naval Technical Research Laboratory in Yokosuka, one of Japan's premier military research facilities. Chief Engineer Nakamura was assigned to lead the evaluation team. He was joined by two other senior engineers. Their mission was clear: reverse engineer the SCR-268, understand its operating principles, determine whether Japanese industry could produce equivalent systems. They expected to find advanced technology that would require study. They did not expect to find what they discovered. The turbocharger system in the P-47 had shocked German engineers with its manufacturing quality. The SCR-268 shocked Japanese engineers for entirely different reasons. It shocked them because it was not trying to be advanced. It was trying to be reliable. It was trying to be maintainable. It was trying to be producible, at scale. And in every dimension that mattered for sustained industrial warfare, it succeeded completely. The antenna system consisted of dipole elements arranged in 3 groups, mounted on a large, aimable cross. The entire assembly was 40 feet wide and 10 feet high. Both the pedestal and the crossarm could be rotated for aiming in azimuth and altitude. Nothing about this design was elegant. Everything about it was practical. The left side of the crossarm contained dipoles, sensitive in angle but insensitive to elevation. 6 dipoles wide, 4 high, each with its own reflector. The right side had a similar arrangement rotated 90 degrees for elevation measurement. This configuration allowed the system to determine both the direction and altitude of targets through a technique called lobe switching. By comparing signal strength from different antenna sections, operators could guide searchlights and anti-aircraft guns onto targets they could not see. At night, in clouds, with accuracy sufficient to bring down enemy aircraft, Japanese engineers understood the principle immediately. It was not revolutionary physics, it was clever application of known techniques. But as they examined the components, the true revelation began. The manufacturing quality was extraordinary. Every vacuum tube was produced to tolerances Japanese industry struggled to achieve even in laboratory conditions. The transformers showed perfect winding symmetry. The resistors and capacitors were standardized, interchangeable components, marked with clear identification codes. An American technician in the field could replace a failed component in minutes because everything was designed for ease of maintenance. This was not prototype quality. This was mass production quality. The Japanese calculated that American factories were producing SCR-268 sets at a rate that seemed impossible. The system was mobile, requiring 4 prime movers to transport the various components. The entire setup, including trucks, weighed more than 82,000 pounds. That the system was mobile at all testified to American industrial capability. Japan could barely transport such equipment between fixed installations. Americans were deploying it to remote Pacific islands, but the true horror lay deeper. Japanese radar development had been fragmented from the start. The Imperial Japanese Army and the Imperial Japanese Navy each ran separate radar programs. They did not share research. They did not standardize components. They competed for the same limited pool of trained engineers and the same scarce materials. Army engineers at the Tama Army Technology Research Institute worked on ground-based radar systems. Navy engineers at separate facilities developed shipboard radar. Neither trusted the other with their findings. This organizational dysfunction meant that Japan was essentially running 2 parallel radar development programs with half the resources each actually needed. The Germans had offered to share their Würzburg radar technology with Japan. They sent complete specifications by submarine at great risk. But inter-service rivalry meant that both the Army and Navy started separate Würzburg development programs. Neither was completed before the war ended. The Americans, by contrast, had created a unified command structure that prioritized radar development across all services. The Radiation Laboratory at MIT brought together the best civilian scientists. The Signal Corps laboratories coordinated military requirements. Private industry, led by companies like Western Electric and General Electric, provided manufacturing expertise. Research flowed freely. Standards were shared. Production was coordinated. The SCR-268 embodied this systematic approach. It used standardized components that were also used in other American radar systems. This meant factories could produce components for multiple radar types simultaneously, achieving economies of scale Japanese industry could not match. Field maintenance was simplified because technicians trained on one system could work on others. The entire approach demonstrated a level of industrial integration that Japan had never achieved. Chief Engineer Nakamura's team worked through the spring and summer of 1942. They disassembled every component. They measured every dimension. They tested every circuit. They drafted detailed technical drawings. They calculated production requirements. And slowly, inevitably, they reached their conclusion. Japan could build a radar based on the SCR-268's principles. Several Japanese Army radar systems, designated Tachi 1 through Tachi 4, were in fact derivatives of the captured American design. But Japan could not build it the way America built it. Japanese vacuum tube production could not achieve the same quality control. Japanese industry could not produce standardized components at the required scale. Japanese factories lacked the precision tooling needed for consistent manufacturing. Even if every technical challenge could be overcome, Japan lacked the raw materials: copper for wiring, aluminum for structures, rare earth elements for specialized components. America had all these materials in abundance. Japan imported them from conquered territories, and those supply lines were growing longer and more vulnerable every month. The report Nakamura's team produced in the fall of 1942 was classified at the highest level. It contained detailed technical specifications. It included recommendations for Japanese radar development, but buried in the measured technical language was a devastating conclusion. America's advantage was not primarily technical. It was industrial. It was organizational. It was systematic. And it was growing wider every month. One section of the report compared American and Japanese production capabilities. American industry was producing radar sets measured in hundreds per month. Japanese production of all radar types combined was measured in dozens per year. American radar systems were being deployed to every theater of war. Japanese radar remained concentrated in the home islands and a few critical bases. American forces were integrating radar with fighter direction, anti-aircraft fire, and naval gunnery. Japanese forces were still learning how to maintain the limited radar sets they had. The contrast extended beyond mere numbers. American radar operators received extensive training on standardized equipment. Japanese radar operators often received minimal training on systems that varied between installations. American maintenance procedures were documented in detailed technical manuals. Japanese maintenance relied heavily on the knowledge of individual engineers who could not be everywhere at once. American radar technology was evolving rapidly, with new models incorporating lessons learned from combat. Japanese radar development was constrained by resource limitations that grew more severe every month. Consider the fate of Japanese attempts to copy the SCR-268. The Imperial Japanese Army eventually produced small numbers of Tachi-1, Tachi-2, and Tachi-4 ground-based tracking radars, all derivatives of the American design. But small numbers meant exactly that. Where Americans deployed hundreds of SCR-268 sets across the Pacific, Japanese forces had perhaps a few dozen Tachi radars scattered among critical bases. Most Japanese anti-aircraft positions continued to rely on sound detection equipment and visual spotting, technologies that were already obsolescent when the war began. The Imperial Japanese Navy developed its own copy of the SCR-268, designated Mark IV Model 1, operating at similar frequencies around 200 MHz. It was intended for searchlight and anti-aircraft gun control at shore bases, but again, production was limited. Manufacturing quality was inconsistent, and deployment was hampered by the same resource constraints that plagued all Japanese military production. Meanwhile, American radar technology was advancing. By 1943, the United States was deploying the SCR-584, a microwave-based fire control radar that represented a generational leap beyond the SCR-268. Operating at 3 GHz using a cavity magnetron from Britain, the SCR-584 featured automatic tracking and integration with the M9 gun director, an analog computer containing 160 vacuum tubes. This system could track targets with precision the SCR-268 could not match, and America was producing it in quantity. About 1,500 SCR-584 systems were manufactured and deployed to both Europe and the Pacific, starting in early 1944. Japan had no equivalent. Japanese engineers understood microwave radar theory. The Japan Radio Company had developed cavity magnetrons independently, but translating understanding into production was beyond Japanese industrial capability. The precision manufacturing required for microwave components, the quality control needed for reliable operation, the integration of complex systems, all of it was possible in theory. None of it was achievable in practice, given Japan's resource constraints and organizational dysfunction. The German experience was similar, but different. Germany had led the world in radar research before the war. They developed the Würzburg radar, considered by many to be the finest fire control system of the war. But German production was hampered by Allied bombing, resource shortages, and Hitler's interference in scientific priorities. Even Germany, with its superior industrial base compared to Japan, could not match Allied production. The gap between Axis and Allied capabilities grew wider every month. What made the situation particularly bitter for Japanese engineers was that they could see what was coming. The SCR-268 captured in 1942 showed them the baseline of American capability. Intelligence reports brought news of newer, more advanced systems. Every captured piece of American equipment revealed manufacturing quality that Japanese industry could not replicate. The mathematical conclusion was inescapable. Japan was not catching up. Japan was falling further behind. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Chief Engineer Nakamura understood something that Japanese military leadership was unwilling to accept. Bushido, the warrior spirit, tactical brilliance, willingness to sacrifice, none of it could overcome an industrial gap that measured not in months but in years. Not in quality, but in quantity. Not in what you could build in a laboratory, but in what you could produce on assembly lines month after month while simultaneously fighting a war across half the globe. The Americans were not just building better equipment, they were building more equipment, and they were improving their designs continuously based on combat experience. And they were training thousands of operators and technicians, and they were documenting everything so that knowledge was not dependent on individual experts. And they were doing all of it simultaneously, in multiple theatres of war, while also supporting Allied forces with equipment under Lend-Lease. This was not warfare as Japanese military doctrine understood it. This was industrial warfare, attritional warfare. Warfare where the side with more factories, more trained workers, more raw materials, and better organizational systems would win regardless of tactical skill or warrior spirit. The SCR-268 taught Japanese engineers what German engineers had learned from the P-47 Thunderbolt. You cannot defeat an industrial democracy at full mobilization through superior will alone. But unlike the German engineers who studied the P-47 inches spring 1943, Japanese engineers studying the SCR-268 inches 1942 were earlier in the war. There was still time, theoretically, to change course. To sue for peace before the gap became insurmountable. To accept a negotiated settlement before American industrial might rendered Japanese resistance futile. That did not happen. Could not happen, perhaps, given the political realities of Imperial Japan. The military leadership that had led the nation into war could not admit that the war was unwinnable. To do so would be to betray everything Bushido represented. And so the war continued. Japanese forces fought with incredible bravery and determination. Japanese tactics often achieved local successes. Japanese soldiers and sailors died by the hundreds of thousands, faithful to their code even as the strategic situation deteriorated beyond recovery. And all the while, American factories continued producing radar sets, aircraft, ships, tanks, artillery, ammunition, and everything else modern warfare required, in quantities that grew larger every month. The Battle of Midway in June 1942 showed what radar meant in naval warfare. American carriers had search radar that provided early warning of Japanese air attacks. Japanese carriers had visual lookouts. The result was that American fighters could be vectored to intercept Japanese strikes while they were still far from the fleet. Japanese defenders, lacking radar, had to rely on visual detection, which gave their fighters insufficient time to gain altitude and position. Japanese analysts after the battle concluded that their lack of radar had been a critical factor in their defeat. But knowing a problem exists and solving it are different matters. Japanese shipboard radar development accelerated after Midway, but production remained limited. The Type 21 air search radar entered service in August 1943. The Type 22 surface search radar with its advanced cavity magnetron became operational in September 1944. Both were indigenous Japanese designs and technically competent. But by the time they were deployed in significant numbers, American forces had overwhelming advantages in quantity and integration. A few dozen Japanese ships with radar faced hundreds of American ships with not just radar but also sophisticated combat information centers that coordinated air defense across entire task forces. The same pattern repeated in every domain. Japanese engineers designed capable systems. Japanese factories produced them in limited quantities. Japanese forces deployed them too late and in insufficient numbers to alter strategic outcomes. Meanwhile, American production accelerated. American technology advanced. American training improved. The gap that Japanese engineers had identified in 1942 did not narrow. It widened. Consider what Japanese engineers learned from examining not just the SCR-268, but every piece of American equipment they captured. In New Guinea, Japanese forces overran American positions and captured supply dumps. They found rations packaged in waterproof containers, medical supplies in standardized kits, spare parts organized in clearly labeled boxes. Everything designed for ease of distribution and use by soldiers with minimal training. Everything produced in quantities that suggested unlimited industrial capacity. The contrast with Japanese logistics was stark. Japanese soldiers often went hungry because supply lines could not keep pace with advances. Japanese wounded died for lack of medical supplies. Japanese equipment broke down and could not be repaired for lack of spare parts. This was not because Japanese soldiers were less brave or Japanese officers less capable. It was because Japanese industry could not produce and distribute supplies at the scale modern warfare demanded. American soldiers complained about their rations. They called sea rations monotonous. They grumbled about spam, but they ate every day. Japanese soldiers in New Guinea starved. Thousands died, not from combat, but from malnutrition and disease, because the logistics to feed them did not exist. American soldiers received new uniforms when theirs wore out. Japanese soldiers patched their uniforms until they fell apart. American soldiers had boots. Japanese soldiers sometimes fought in cloth shoes. This material disparity extended to every aspect of warfare. American forces had reliable radio communications down to the company level. Japanese forces often relied on runners and signal flags. American artillery had abundant ammunition and could provide massive fire support. Japanese artillery rationed shells. American aircraft had sophisticated instruments and navigation aids. Japanese aircraft had basic instruments and pilots, navigated by compass and landmarks. The engineers studying the SCR-268 understood that each captured item told the same story. America was not fighting with superior technology alone. America was fighting with superior systems, superior organization, superior industrial philosophy. And underlying it all was an industrial base so vast that the very idea of scarcity seemed foreign to American military planners. Japanese radar development continued throughout the war, driven by engineers who understood the desperate need for modern detection systems. The Imperial Japanese Army developed the Tachi series ground-based radars. The Tachi 3, based on British good luck sets captured at Singapore, saw the most extensive production with 150 units, built by Sumitomo, entering service in early 1944. The Tachi 6 Type B fixed early warning device operated at 3 meters wavelength with 60 units built by 1943. The Tachi 18 Type B portable early warning device saw the widest deployment with 400 units produced. These numbers sound substantial until you compare them to American production. The United States produced approximately 3,000 SCR-270 and SCR-271 early warning radars, about 900 AN TPS-3 portable radars, over 1,500 SCR-584 fire control radars, thousands of shipboard search and fire control radars, thousands of airborne radars for night fighters, patrol aircraft, and bombers. The scale difference was not incremental, it was exponential. Japanese naval radar development followed a parallel track. The Type 21 air search radar, operating at 150 MHz with 5 kilowatts peak output, could detect aircraft groups at 100 kilometers and single aircraft at 70 kilometers. First fitted to the battleship Issei in April 1942, at least 30 to 40 sets were built and used operationally. The Type 22 surface search radar, operating at 10 centimeters with a 2 kilowatt magnetron, represented Japan's most advanced radar design. First fitted to destroyers in March 1942 and to capital ships later that year, about 300 units were produced. 300 Type 22 radars, Japan's most successful shipboard radar, deployed across the entire Imperial Japanese Navy over 3 years of production. The United States Navy in the same period deployed thousands of SG surface search radars, SK air search radars, and specialized fire control radars. By mid-1944, every American destroyer, cruiser, battleship, and carrier had multiple radar sets. Most Japanese ships still relied primarily on visual detection, supplemented by limited radar coverage. The Battle of the Philippine Sea in June 1944 illustrated the cumulative effect. American carrier task forces had comprehensive radar coverage. Combat information centers coordinated air defense across the entire fleet. American fighters were vectored by radar to intercept Japanese strikes far from the carriers. Japanese aircraft, attacking in large formations, were detected at extreme ranges and systematically destroyed by radar-directed fighter interceptions and radar-directed anti-aircraft fire. The Japanese lost over 400 aircraft in 2 days. The Americans called it the Great Marianas Turkey Shoot. Japanese pilots called it slaughter. Japanese defenders tried everything. They developed chaff, which they called deceiving paper, invented by Navy Lieutenant Commander Sudo Hajime. It was used with some success to confuse Allied gun-laying radars in the Solomons in 1943, but aluminum was too scarce for large-scale chaff production. Japan had to choose between using aluminum for aircraft construction or for radar countermeasures. There was never enough for both. They attempted radar jamming, but American post-war analysis dismissed Japanese jamming as essentially non-existent. Japanese engineers designed systems that never made it to production. They worked on radio energy death rays that consumed resources without producing viable weapons. The Würzburg radar technology Germany had sent by submarine at such great risk remained in prototype stage when the war ended, because Japanese industry could not produce vacuum tubes of sufficient quality to make it work. By late 1944, as American forces closed in on the Japanese home islands, the technology gap had become a chasm. American B-29 bombers attacking Japan carried sophisticated radar systems. The AN/APQ-13 radar allowed bombing through clouds. The APR-4 intercept receiver, manned by a crewman called the Raven, detected Japanese radar emissions and helped bombers avoid defended areas. Some aircraft carried ARR, 5 communications search receivers to monitor Japanese radio traffic. Japanese defenders had radar, but it was insufficient in quantity and capability to coordinate an effective air defense. The Type 42 radar and its improved versions, the Mark IV Model 3 and Mark IV Model 4, were effective fire control radars when they worked. American evaluation of captured units found them capable of fully blind anti-aircraft fire direction, but there were too few of them. Most Japanese anti-aircraft positions still relied on sound detectors and visual observation. Against aircraft flying at 30,000 feet, often above clouds, these methods were worse than useless. Japanese fighters equipped with radar could theoretically intercept B-29 seconds at night, but the Imperial Japanese Navy never got airborne intercept radar into operational service, despite years of development. The Imperial Japanese Army worked on night fighter radar but achieved similarly limited results. A few experimental installations were tested. None became operational in numbers sufficient to matter. The strategic bombing campaign that destroyed Japanese cities proceeded with minimal interference. Not because Japanese pilots lacked courage, not because Japanese ground crews lacked dedication, but because the systems needed to coordinate night fighter interceptions, to vector fighters onto targets, to direct anti-aircraft fire effectively. Those systems existed in American and British service by the thousands, and in Japanese service hardly at all. Post-war interrogations of Japanese radar personnel revealed the depth of their frustration. Officers and engineers stated flatly that at night or in bad weather, when American aircraft disturbed their radar detectors, they could not and did not shoot effectively. Around the Sasebo Naval Base in western Kyushu and in Formosa, they claimed better success through more practice. But in the critical areas defending Tokyo and other major cities, Japanese air defense was largely ineffective. Captain Idura of the Naval Technical Department admitted that Japan's only hope was modification of their shipborne 10-centimeter radar for air defense use, and if that proved susceptible to jamming, then we could not see the way for defense. He and other officers were frank that modification of any radar system in the last months of the war was next to impossible. The industrial infrastructure was too damaged, the trained personnel too few, the materials too scarce. This was the reality that Chief Engineer Nakamura had foreseen in 1942 when he first examined the captured SCR-268. He had seen American manufacturing quality and understood that Japan could not match it. He had calculated American production rates and understood that Japan could not compete. He had recognized that the war Japan entered was not the war Japan could win. Industrial warfare at global scale required industrial capacity at global scale. Japan had never possessed it. America had it in abundance and was expanding it every month. The atomic bombings of Hiroshima and Nagasaki in August 1945 are often portrayed as the decisive factor that ended the war. But they were really the final demonstration of what Japanese engineers had learned 3 years earlier from studying a captured radar set. America could develop, produce, and deploy weapons of unprecedented complexity while simultaneously fighting a global war. The Manhattan Project employed over 130,000 people at its peak. It built massive industrial facilities. It solved unprecedented technical challenges. And it did all of this while also producing ships, aircraft, tanks, radar, and everything else the war required. Japan had attempted its own nuclear weapons program. Multiple programs, actually, as inter-service rivalry, meant both the Army and Navy pursued separate research. Neither achieved anything approaching a working weapon, not because Japanese scientists lacked understanding of nuclear physics, but because building atomic bombs required industrial infrastructure and resource commitment that Japan simply did not have. The engineers who examined the SCR 268 inches, spring 1942, had encountered a paradox. The radar itself was not the most advanced technology of its time. Britain had more sophisticated radar in some applications. Germany had developed excellent systems. Even Japanese engineers had made important contributions to radar theory. But what made the SCR 268 devastating was not its technical sophistication. It was its manufacturability, its reliability, its maintainability, its integration into a comprehensive system of air defense. The Americans had solved a problem that Japan never properly understood. Modern warfare was not about building the perfect weapon. It was about building good enough weapons in quantities sufficient to deploy everywhere they were needed, to maintain them under field conditions, to replace them when they were lost, and to continuously improve them based on combat experience. The Americans called it logistics. The Americans called it systems integration. The Americans called it industrial mobilization. The Japanese called it impossible. Consider the post-war assessment. Japan built approximately 30 different types of radar sets during the war. Total production across all types was approximately 7,256 units. This sounds substantial until you realize that the United States produced individual radar models in larger quantities than Japan's entire wartime production of all radars combined. The disparity was not 2-to-1 or even 10-to-1. In many categories, it approached 100-to-1. Japan's electronics industry after the war rebuilt itself through technology transfer from the West. Sony, founded by technically trained engineers, Masaru Ibuka and Akio Morita, recognized the substantial technology gap between Japan and America. They became the first Japanese company to collaborate with Western Electric in 1953. They imported transistor technology and built it into commercially successful products. Other Japanese companies followed similar paths, licensing Western technology and building competitive industries. But during the war, such cooperation was impossible. Japan fought in isolation, cut off from technological exchange with the only power that might have helped them, Germany, whose assistance arrived too late and in insufficient quantity to matter. The result was predictable: an industrial power of the second rank attempting to fight industrial powers of the first rank in a war where industrial capacity was the decisive factor. The engineers who studied the SCR 268 became prophets of defeat, though their prophecy went unheeded. They wrote their reports in measured technical language. They documented American capabilities. They recommended Japanese responses. But underlying every recommendation was an impossible requirement: catch up to an opponent who was not standing still, who was improving faster than you could. Copy, who could produce in a month what you could produce in a year. One of those engineers, whose name remains buried in classified archives, supposedly said something to a colleague that was recorded in a personal diary discovered decades later. We are examining how they make steel by studying a katana blade. We understand the sword. We do not understand the forge, the ore, the fuel, the craftsmen, the apprentices, the traditions, the entire system that produces swords. And they are not making swords. They are making steel beams for skyscrapers, 10,000 times as much steel, and we are still discussing the proper way to fold metal. This is what the SCR 268 taught. Wars are won not by the best engineers, but by the best industrial systems, not by the most brilliant designs, but by the most producible ones. Not by what you can build in a laboratory, but by what you can manufacture on assembly lines while your cities are being bombed. The Japanese built for quality when they needed quantity. They built for elegance when they needed reliability. They built what they could afford when they needed to build what victory required. The Americans built SCR 268 radars by the hundreds, then replaced them with better systems by the thousands. They built systems designed for mass production, designed for field maintenance, designed for operation by minimally trained personnel. They built redundancy into everything because they could afford to waste resources in pursuit of certainty. They built industrial democracy's weapons, the physical manifestation of what free societies could produce when threatened. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The captured SCR 268 radar that Japanese engineers examined in spring 1942 still exists in fragments, scattered across museums and private collections. When historians study it, they are not just looking at obsolete technology. They are looking at the moment when one nation confronted the mathematics of its own defeat and could not change the equation. The assembly lines that built radars in peacetime built victory in wartime. The workers who built consumer electronics built the weapons that ended empires. The factories that made radios made the systems that coordinated the destruction of fascism. Japanese engineers were right to fall silent when they opened that radar set and saw inside. They were not just looking at superior manufacturing, they were looking at their future and finding none. The SCR 268 did not win the Pacific War alone, but it revealed the truth that decided the war's outcome. You cannot defeat a mobilized industrial democracy through spirit and sacrifice alone, because democracies, when truly threatened, transform their productive capacity into weapons on a scale that authoritarian regimes cannot match. They were just engineers assigned to evaluate captured equipment, until they opened the SCR 268 and realized America was not just ahead. America was operating in a different paradigm entirely, building not weapons but weapon systems, building not radios but radar networks, building not components but complete industrial capabilities, and building all of it at scales that made Japanese production look like laboratory prototyping. That is what made the SCR 268 not just a radar, but a revelation. 8 years behind in electronics, Nakamura had said. But the truth was worse. 8 years behind in capability. Decades behind in industrial philosophy. Forever behind in the one resource no amount of warrior spirit could replace: time. Time to build factories, time to train workers, time to develop systems. Time that Japan had spent conquering territory when it should have been building industrial capacity. Time that ran out in August 1945, when the mathematics of industrial warfare reached their inevitable conclusion. The radar sat in that testing chamber in Yokosuka. Its circuits silent, its purpose fulfilled. Not to detect aircraft, not to guide guns, but to teach one final lesson to engineers who understood what their leaders refused to accept. In modern warfare, the side with more factories wins. Always, inevitably. Mathematically. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.